Hey guys, hello everyone. Welcome to Rasayan Academy, all of you. So I hope that you have been watching the series of some very important and basic topics that we have started with. Right, these are all the topics which constitute the general organic chemistry. For example, the acid and base concept, IUPAC nomenclature. We are also going to be discussing just after this. We will be discussing aromaticity and important examples of aromaticity, right? And I hope that these are going to help you in your upcoming examinations. Also guys, in the previous video which was on the pKa concept, I hope that you have seen the video. It was a very small video, right? And I also suggested you to study chapter number 8 from Claydon, which is going to give you very much knowledge of all the aspects of acidity and basicity. So we apply that knowledge and we try to solve some questions from the CSIR net examination. So these are some CSIR net previous year questions. First one is from June 2011, very simple one. The question is asking us the correct order of acidity of the following compound from A to C is. Now firstly you are going to try it by yourself and then I will answer. Alright guys, so correct order of acidity. Acidity will be high. Acidity is directly proportional to stability of conjugate base. So if the base is stable, if the conjugate base after the removal of a proton is stable, then the acidity is going to be very high. So that is the factor which is going to determine the answer. First thing, for option number A, if we remove a proton from here, that is going to give you a negative charge. Right, where is the negative charge? Exactly over here. If we remove a proton from here, you will get a negative charge, and if we remove a proton from here, you will get a negative charge as well. So comparing the stability of all of the conjugate bases, which is going to be the most stable? A is going to be the most stable over here. Why? Because first of all, it is aromatic in nature. It is aromatic in nature, and secondly, there are very electron withdrawing groups connected over it. So it is going to form the cyclopentadienyl anion, alright, which is going to follow the Huckel's rule, and it is aromatic. Option number C is also aromatic in nature, right? But since there are methyls are not going to be electron withdrawing, so it is going to be less stable. The conjugate base of C will be less stable than A, but still it is more stable as compared to B, because B is going to follow 4n pi electron rule. 4n pi electron rule means it is going to be anti-aromatic. Alright, so it is anti-aromatic, and the molecule does not want to become anti-aromatic, so this is going to be least acidic. Alright, so the original compounds in option number B, this is going to be least acidic, A is going to be most acidic. So we can see A and B, these are the two extremes, and then C is going to be in middle of them. So answer is option number C. Moving onwards, the correct order of basicity for the following anions is. Order of basicity of the following anions. So we once again discuss the same concept, that is stability of conjugate base. This is going to be inversely proportional to the basicity of the conjugate base. That is, if the conjugate base, which is the anion basically, this anion has definitely come from a phenol. Phenol, for example, let's say this is the phenol we are talking about, or let's say it is orthonitrophenol. Alright, so the acidity of the phenol is going to determine, greater the acidity, this is proportional to let's say more acidic, which means it is going to be less basic. Alright, so acidity of the phenol is going to determine how basic it is. If it is more acidic, then the conjugate base is going to be less basic, like that. And if the stability of conjugate base is high, then also the basicity will be less. So let's look at all of these anions. If you just want to go by the stability, you will say that the option number 1 and option number 3, these are going to be more stable. Why are they more stable? Because there is minus R effect of nitro in both the ortho and para position. In option number 2, it is only the minus I effect which is going to work. So 2 is going to be, let's say, most basic. 2 is going to be most basic, which is present in option number A and C. So B and D are wrong because 2 is going to be the most basic. This is going to be the most basic. Now what after that? Who is going to be more basic from the other? So as we see guys, the O minus, the negative charge is distributed into the nitro which is present on the ortho group. So here you have a minus R effect as well as a minus I effect, which is going to be greater than the minus I effect at the para position. So we can say that 1 is going to be more stable as compared to 3, and that's why 3 is more basic than 1. So your answer is option number A regarding this question. Alright guys, so in this particular question we are talking about the increasing order of pKa values of the circled hydrogens in the following compounds is. So these hydrogens we are talking about, all the circled one, right? So if we consider their acidities, or first of all, for considering the pKa value, we'll consider the acidity because we know that pKa is inversely proportional to acidity. All right, if you want to see this question by yourself, please try to check it out first and then see the solution. All right, yes. So first thing guys, we are going to discuss that what is going to be the stability of the conjugate base. All right, and also there is a positive charge over here. Correcting this question, there is a positive charge over here. Right. So what is going to be the stability of the conjugate base? In question number, in the option number 1, as you see that if you are, let's say, removing this proton, if you remove this proton, it is absolutely going to be conjugated into the carbonyl, right? Not into this carbonyl because this is an amide carbonyl over here. So there's going to be a constant electron resonance from the nitrogen. So this is going to give the electron density over here into this carbonyl. All right. Next is you are having something similar to guanidine. You can call it cyanoguanidine as well. All right. So both of these are protonated, which means that there must be a positive charge on this. Let's say there is a positive charge on this nitrogen. All right. And there's a double bond over here. And this proton will be lost. After that, you will get a negative charge. So this negative charge is actually going to help in the removal or quenching this positive charge on this nitrogen. And it is also a stable, very, very stable conjugate base, right? So yes, now what is next? Next we have imidazole molecule, in which we are talking about the removal of a proton which is not going to do resonance, right? The negative charge over here, it is outside the ring guys. The proton has been lost from the sp2 hybridized orbital like this. So this is not going to do resonance within the ring. Even if there is a positive charge over here, there's a huge minus I effect, that's fine, but it is not going to do the resonance. So 3 is going to be least acidic. Who is going to be most acidic? This one, option number 2. This is going to be, this proton is going to be most acidic. And this one is going to be intermediate because here the stability is only by doing resonance into this carbonyl. Alright, or you may also consider the resonance into this carbonyl as well, but this is not having the extra stability which this system will have because it is going to have similar resonance structures. Alright, cyanoguanidine system. Alright, so 2 is going to be most acidic, and that is why the least pKa value, which you have in option number C and D. Alright, A and B are absolutely wrong. So in option number C and D, you have this. Let's move onwards. Then it is going to be least acidic is going to be this, which means maximum pKa value. So this is going to have maximum pKa value, and 1 is going to be intermediate. So C is the correct answer to this question. Moving onwards, guys, the decreasing order of basicity of the following compound is. So we look over here in this molecule, that is decreasing order of basicity is asked. So which proton is going to be most available, right? Or let's say which nitrogen lone pair is going to be most available. That is going to be most basic. We are going to look for most available lone pair. All right. Yes, so let's look at the first example over here, guys. We see that the lone pair on this nitrogen This nitrogen is specifically known as the pyrrole type nitrogen, and this nitrogen is known as the pyridine type nitrogen. All right. So why is that? So because this is going to undergo resonance in this way. All right. And the nitrogen, the other nitrogen over here, it is not using this electron pair into resonance. However, it is accepting electron density in this way. So this is going to be a more nucleophilic center or basic center in this molecule. You can say that imidazole. Okay. What about the second one, guys? Here it is not an aromatic system, but definitely the electron density is being pushed away. So this is a more basic nitrogen as compared to this. Similarly, this system is once again similar to guanidine system, guys, which is going to make by resonance, which is going to make from both the sides this nitrogen as a more basic center. All right, and here you are having the push by two different nitrogens. Here you have by only one nitrogen. So it is very evident that 3 is going to be more basic than 2. Rest we are going to see, but 3 is absolutely more basic than 2. All right, and these are what? Saturated. The rings are saturated over here. Here the ring is unsaturated, and you have to use the lone pair of this pyrrole for making the ring aromatic. So this is one is going to be less basic. It is going to be less basic than whom? Than the 2 and the 3. All right, but it is going to be more basic than 4. Why? Because pyridine nitrogen is on a sp2 car or sp2 nitrogen. That's fine, but also it is only one nitrogen, and here this nitrogen, the pyridine type nitrogen, is also assisted by the pyrrole type nitrogen like this. So here you get still better assistance as compared to this, and that is why 1 is going to be greater than 4 and 3 is greater than 2. Just by understanding these relationship, you can answer the question. These questions, guys, are making the basic of organic chemistry, and you cannot do without doing these concepts. Okay, ये foundation है organic का, so you have to do the foundation. Yes, next question. The correct order of pKa value for the compounds X, Y, and Z is. So here you see, guys, X, Y, and Z. pK value once again. So we will find the acidity order and then we will do the inverse for the pKa. So what do you think? Which is going to be the most acidic? That is your first question. Most acidic, you can see over here. Why has to be the most acidic? Because when the proton is lost, it is going to give you a cyclopentadiene anion that also stabilized by 5 cyanides. So this is absolutely the most basic, most acidic without any doubt. Next is you have X and Y over here. So which of these two is going to be more acidic, X or Y? Yes, if you remove this proton, it is once again going to give you resonance in both of these carbonyls only, but the resonance is limited till carbonyl. Right. What about this, guys? Z. It looks like that if you remove this proton from here, from the central ring, then the overall compound might become aromatic, isn't it? It looks like that. What will be the electron count? 6 and 6, 12 plus 2, 14. So there will be 14 pi electrons, isn't it? So 14 pi electron follows the Huckel's rule. Right, but it is not going to be aromatic. Why? Because you cannot say when you are having different rings, you cannot say that this anion is going to be, carbanion is going to be aromatic, because aromaticity is the property of one single ring. So these two rings are already aromatic. They don't need the negative electron density, right? So that is why this negative charge is just going to behave like a negative charge which is isolated, but it is only having resonance possible within two phenyl rings. It is not going to have the extra stability of aromaticity, not at all. So it's going to just be resonance stabilized by two phenyl rings. So what is the order of acidity? It's going to be Y greater than X greater than Z. Z is the last, guys. We call this effect as ring annihilation effect. Okay, we are going to study this in the next session where we are going to study aromaticity. Yes, guys, I am going to explain the each and every single detail of aromaticity and all the important questions which have been asked in the previous years. Okay, so just wait for that. I'm bringing all for you. We are also going to break down organic reagents, but that's going to take a little bit of time. But first we are going to do aromaticity, right? So what is happening over here? Y is greater than X is greater than Z. This is the order of acidity, and the pKa is going to be just the reverse of this. Z is greater than X is greater than Y. Alright, in this way. So answer is option number C. So we move onwards and we see another question. Correct order of basicity of the following heterocycles. How are you going to check? You see pyrrole type nitrogen, which means it is going to use up the electron density to become 6 pi electrons. So these electrons are no more available on this nitrogen. Similarly, here also these electrons are no more available on this nitrogen, but here this nitrogen can be electron rich. Yes, why not? And similarly, this nitrogen is also going to help the other one in being more basic. Now, A is going to be the least basic that you have understood, but what is the competition between B and C? Who is going to be more basic? Right? A is the least basic, but then from the options you get this one as the answer, so easy. But right, but what happens is, guys, when you are looking at B and C, you check that the minus I effect of the nitrogen is more on option number B, because the distance is less, they are closer to each other, right? And here they are far away from each other. So C is going to be more basic than B and then A. This, there are two reasons for it. One of them is the minus I effect of this nitrogen, and the other one is that third position is always more electron rich as compared to the second position, right? So that is why, because of the electron flow is like that, this one is going to be more basic. Okay, now guys, we move on to a question which is actually using the pKa concept. Alright, which I have already made a video on. Please check it out. The pKa values of the following salt of aspartic acid are indicated below. The predominant species that would exist at pH is equals to 5 is. So one thing, guys, here it is a question of amino acids, natural products. You know that. But the concept is the pKa concept. Right, the concept is nothing new. What is the structure of aspartic acid? Let's say the structure is given over here. Aspartic acid is the one which has a acidic side chain. Only one carbon in between, an acidic side chain like this. So what are the pKa values of all of the different groups? See, whenever the pKa is mentioned, you have to take the acid in the all protonated form, because then only you will one by one do the deprotonation, isn't it? If it is already deprotonated, you will be confused. So you have to take them in the all protonated form, like this. Right. Now, pK values of the following, acha, theek hai, it is going to exist at pH is equals to 5. How is it going to exist? So there was a condition that the pH, if it crosses the pKa value, then the concentration of the conjugate base is going to be greater than the than the concentration of the acid itself. Because then you say that the acid has started to actually deprotonate. When the pH is equals to pKa, then you say the concentration of the anion is exactly equals to concentration of the acid. When the pH is less than pKa, then concentration of acid is obviously more. So here I have just crossed, pH value is 5, and let's see whose value it is crossing. Absolutely, it is not crossing the 9.9 value, so we are not going to deprotonate it. It will be as it is, like ammonium. Alright, so yeah, let's just make some space. So this is not deprotonated because the pH value is not crossed. But for both of these conditions, pH value is greater than pKa. Isn't it? pH is 5 and it is greater than 2.0 and 3.9. So both of these acids will be deprotonated and the ammonia will be as it is. And as you see, the answer could be this. Alright. Yes, what is wrong with this option A? It is wrong because you have one acid still protonated. What is wrong with option number C? Here you see ammonium ion is deprotonated. Cannot happen, guys. 9.9 value is not crossed. Similarly, here this is still protonated. Absolutely does not make sense. So when the pH is greater than pKa, it will be deprotonated. That easy. Similarly, a question on tyrosine. At tyrosine, pH is equals to 12. How is it going to exist? So guys, for tyrosine, you have to know the structure of tyrosine, isn't it? To be able to know the structure of tyrosine. It is actually very easy. You can just classify the amino acids and then remember their structures, right? Classify them according to having a aromatic side chain, acidic side chain, and so on. All right, so what is the structure, actual structure of tyrosine? You have a benzene ring to which alcoholic OH is connected, the phenolic OH basically, and then you have, let's say, NH2 and COOH. Once again, you are having the alpha amino acid. So this is how tyrosine is. Okay. So since we are talking about the deprotonation or how it is going to exist, we will write this in the all protonated form. This is the all protonated form of tyrosine. Right. Now guys, what happens when you are placing them in the pH 12? Here the pKa values of all of these groups are not mentioned. So what are you going to do? You are going to assume that pKa of the carboxylic acid is somewhere around 3.5 to 4, somewhere in between this. So you're going to imagine that, assume that, because it is the same value. For the ammonium ion, the pKa value is somewhere around 9 to 10. And for the phenolic OH also, usually the pKa value is greater than 10. But yeah, it's going to be in between 10 to 11 only. Alright, so what should be the answer? Whose pKa value is pH 12 crossing? It is crossing all the pKa values, isn't it? It is crossing pH is equals to 12, is crossing all the values. So we must get all of them deprotonated. Do we have an option like that? Let's see. In option number A, this ammonium ion is still protonated, so which means this is absolutely wrong. In option number B, we have all of them deprotonated. Ammonium goes to NH2, COO minus, O minus, all of them are deprotonated. So we will just keep this on hold and we'll see the next one. Option number C, OH is not deprotonated. However, these two are deprotonated. Here O minus and NH3 is still plus, so absolutely wrong. So we can decide between option B and C that how you are going to say at pH equals to 12, how will it exist? It will exist like this because all the values are crossed, right? So do we have to remember these values? Yes, a little bit. A little bit we have to remember. All right, guys. So now we are going to basically move on to another session. This is the last video where we are discussing the pKa concept. And yes, absolutely, we will be doing more and more questions, previous year questions. Once we have done all of the basic organic chemistry topics, we will do all the questions collectively. Next topic that is coming is aromaticity, and it's going to see you all very soon. So take care all of you guys and keep studying. Bye everyone. Keep practicing guys.